which used a lot of methods taught in classes like stochastic calculus class, risk management class, and derivative class. So the outline is first I spent a lot of time going through the Longstaff and Swartz paper and used their American Monte Carlo approach for the American option pricing. And for the simulating process, I first tried with the geometric Brownian motion, and then later at the project I switched to test model, which accounts much better for the volatility. And for the European, I used the Black-Scholes model. Then I compared the pricing difference between the European and American put options, and there are different sizes of discount rates and also different prices. And then I went back to the basis function selection in the Brownian motion with American Monte Carlo model. I used a quadratic polynomial. So I went back and tested it to check if there is a better choice for the basis. And then in the end, I did a comparison between the geometric Brownian motion and testing with American Monte Carlo pricing. And once again, I have to briefly walk through the Longstaff and Swartz paper, which is one of the best approach for American Monte Carlo, and also I think the most fundamental approach, I believe. And just for a simple example for you to get it straight, first we generate 8 paths of prices using Brownian motion. This is learned from this stochastic calculus class, and we also have 4 sets of 10 points, which is 0, 1, 2, 3. Then we use the price at time 3 to get the intrinsic value of the put options at time 3. Then we label all the price points, whether it's in the money or not. And then for time 2, if it's in the money, then we discount the intrinsic price on the time 3 on this path back to time 2 and use it as the target variable for the regression. And here we are using the quadratic polynomial for the regression, as it is like most often used in cases like this. We will look further into like how good or bad the quadratic is later. So we now have the coefficients after the regression, so we can estimate the continuation value at time 2 for time 3, aka the discounted future payoffs at time 3. And now we compare the intrinsic value at time 2 with the continuation value. If the intrinsic value is larger, we just exercise it at time 2. If not, we hold it till time 3. The final value at time 3 is just the intrinsic value at time 3, since there is no more future points. And then we repeat the whole process again for all the other time points, then discount all the cash flows of each time point back to time 0, and then take the average of all the paths. So in this example, we just take the average of the 8 paths. And here is an outline of the process we just went through. And later, I'll just integrate all those steps into one single function. And for the geometric Brownian motion, those are the parameters you need for the path simulation. I think if you've taken the stochastic calculus class, you're pretty familiar with those parameters. And yeah, this is a code. Sorry about the code for the Brownian motion. And these are the parameters we need for the Monte Carlo process we just mentioned. And yeah, this is how it looks in Python code. And this is how European looks, which compared with the American option, you can see that European is much simpler since it's considering the volatility without different paths. And after building the model, I started with a simple comparison as sponsor Peter suggested. And those are the numbers of the parameters I picked, which I discussed with Professor Brockton, who taught the derivative class. And those were the rationales behind. He thinks it makes a lot of sense for most typical stocks in the current market. And oops. And um, on the left, it's the result for the pricing difference. The American put is priced higher than the European put, which is expected, since American option provides the holder the flexibility to exercise at any point. In most cases, while the European only allows exercising on the expiration date, which provides extra value to the asset. And on the right, it's a graph inside the American Monte Carlo model. We just walked through for the simulation path. With a sigma of 0.23, we can see this typical shape of stochastic path. Which means it's working pretty good, working as expected. As you can see, there are up and downs in the plot. And for a set of different option prices, just as Peter suggested, the American option is never cheaper than the European option, as American option gives extra flexibility to exercise, which is pretty valuable. And both of them converge to zero because the intrinsic value approach zero as the underlying price increases. And for a set of different rates, they both decrease at the rate increase, just as expected. I try to capture the sensitivity, but it's not significant. There's more change, like up and down to the American, like more volatility, but on average, it's not significant. And here is where I go back to when we were building the American Monte Carlo model. We mentioned basis, which is the number of basis functions used in the polynomial regression. We used quadratic as it was used by the Longstaff and Schwartz American Monte Carlo paper. And then it was, or say it still is, commonly used in Monte Carlo simulations to capture the nonlinear factors. And from the plot, we can see that from 2 to 5, this rapid decrease just suggests that increasing the model's complexity initially helps in capturing more dynamics between 5 to 10. There are some like fluctuations, which can be seen as the sensitivity of the model to those specific basis numbers, possibly reflecting overfitting or like instability in the regression. And after the number of 10 bases, it turns to be stabilized and slowly increasing, which means to this point, adding more bases to the model does not significantly change the prediction of the model. So from a math point of view, the best choice for the model is about 10 bases. If we have like enough computational power, increasing the number of basis functions can potentially improve the regression's ability to capture more complex patterns. But like from a financial engineering point of view, a nonlinear factor with the power of 10 is generally not realistic. And that's the power often seen in astronomy, not finance. So too many basis function can lead to overfitting problems also. For the differences, Brownian motion assumes a constant volatility, which is the sigma that we mentioned earlier. Hesston model, on the other hand, treats volatility very differently. It treats volatility as a stochastic process. It has a more realistic way to handle volatility, which involves like fluctuations and mean reversion parameters like kappa, theta, and eta. If you have taken the risk management class taught by Professor Haibei, you know what those offers in terms of like the complexity in a model. And Richer dynamics, Hesston has the incorporation of stochastic volatility and its correlation with stock price movement. And like parameter Zo in the Heston model allows capturing scenarios where rises in volatility correlate with the drops in stock prices, which is very common during market downturns. And Heston can also reduce overfitting. So Heston model inherently includes the additional sources of randomness. It does not depend very much on the basis function, on the number of bases to capture patterns. It will be talked more about this later. And those are the parameters I mentioned. Some of them I mentioned some of them in the last slide. The highlighted parameters are the main difference between the two models. And yeah, this is a code. And for American Monte Carlo, I used polyfit, like polyfit function to let it to find a optimal basis by itself. And the basis is never more than the number of 6 upon checking, which is great, compared with the optimal basis which is seen with the American Monte Carlo using Brownian motion, which is more than 10 in the Brownian case. And then I try to set the parameters to make the two models as equivalent as possible. For example, I set the initial volatility, which is V0 for the parameter name, and theta to be 0.0529 in Heston, to be exactly the square of the sigma in the Brownian motion, which is 0.23, and also eta to be set to 0.23. But no matter like how hard I try, how equivalent they are in terms of parameters, the two models always cross, like you can see from the plot around the middle point of the graph. And we can sort of see the different sensitivity. The Heston model adapts to the change of stock prices more dynamically, especially at lower prices where the most volatility tends to be in a put option market, which affects the put option prices more significantly. On the other hand, the geometric Brownian motion model has fixed volatility, which is less responsive to the change in the stock price, especially noticeable like at lower levels where we would generally expect a higher volatility impacts in the real market conditions. And yep, there are still a lot of aspects to dig into. I have included some of the possible future directions into